Hello everyone, I'm Norman Welberger, and thanks for joining me on this adventure towards solving general polynomial equations. Today, we are going to go right back to the beginnings of this adventure, where we started looking at the quadratic equation in a somewhat new way. Now having quite a lot of experience and quite a few results under our belt and a pretty good idea of how to look at things generally, it's great to go back to that quadratic equation and reinterpret it in the light of what we know. So we're going to be able to see this quadratic equation in new eyes. And I remind you that this is really a central historical question in algebra. Okay, so the usual story is that we start with a quadratic equation, say 0 equals c0 minus c1x plus c2x squared. So I'm returning more or less to the notation that we started with, these coefficients, c0, c1, c2, but crucially, we're putting a minus sign in front of the coefficient of x. We know that's actually a better way of proceeding. Okay, the standard recipe that everyone memorizes gives us two solutions in terms of square roots. Okay, here they are. C1 plus square root of c1 squared minus 4c0 c2. That's the discriminant inside the square root there. All of that divided by 2 times c2, and a similar one with a minus sign instead of a plus sign. Okay, now of course this is valid provided that the denominator here, c2, is non-zero. And of course, finding square roots is then the essential question. So this is a way of transforming the general equation to one for solving perhaps the simpler equation, x squared equals something. Now, finding approximate square roots is something that people have been engaged with for thousands of years. The ancient Babylonians had an algorithm for finding square roots. And this is an important kind of ingredient in algebra, which of course is a little bit lost to our modern students. But nevertheless, we rely on calculator to do it. Okay, now what we have, however, is a very different way of thinking about this. Okay, so here is our alternate form. We're calling it the geometric form of the quadratic equation, where we write an equation of the form g of x, let's say, equals 1 minus x plus t sub 2 x squared equals 0. So the c0 and the c1 have both been replaced with 1s, and we're using t2 instead of c2 for various reasons that you'll be familiar with. Okay, and we know that this is just a very special case of this grand problem that we are able to solve. And in this special case, our solution is given in terms of a power series. Say x is equal to f, which involves these coefficients. So these are the RSP numbers in the very simple case when there's only one variable, m2. So it becomes 2m2 factorial over 1 plus m2 factorial. And we recognize this is a Catalan number. And so the associated series is f, which is the sum as m2 goes from 0 up onwards of r of m2 times t sub 2 to the m2. And here's how that series starts out. So it's basically the Catalan numbers strung together with increasing powers of t2. Now, this, of course, is nothing new. This understanding it has been around for a long time. People have long recognized that this particular power series is essentially capturing a square root in some sense. And we're sort of exploiting something that we already know. So now suppose we take this thing, and just to be specific, let's go up to terms of degree 10. Okay, then this ongoing series becomes just a finite polynomial. Here it is f of t2, let's call it, from 1 up to 16,796 t sub 2 to the 10. Now, if we plug that into g of x, let's just check. We check that g of better define these things. So there's g. We will define that. And here's f of t2. We'll define that. Let's just check our definitions. G of x and f. Okay, there they're both defined. Now let's calculate g of f of t sub 2. Okay, maybe put that in a new line. Okay, what is that actually equal to? Let's evaluate it. So what do we see here? Okay, there's the t2 times the f squared. There's the minus f, and I guess the ones have canceled. So we see that there's, these are the sort of the original thing before we simplified. Okay, so now let us simplify this. What do we get? We get t sub 2 to the 11 times various other terms. So this is a polynomial which is starting with 11th powers. That means that, so that actually verifies, this verifies that indeed g of f sub 2 equals 0 up to terms of degree 10. And that's our preferred interpretation of how we're dealing with these power series. We're not thinking of them as functions. We're thinking of them as generating functions, as formal series like the combinatorialists do. And we want to interpret statements about them up to a certain degree, where that degree is variable. So we can also run this again for a degree 20 or a degree 100 or anything else. Okay. All right, so this is definitely an algebraic solution. But we want to move towards also finding numerical solutions. And we also want to go back to the more general form, because after all, this is more specialized than our original one. So let me remind you how we can sort of go back and forth from the general quadratic to this more specialized geometric one. Okay, it involves some certain changes of variables that we talked about, I think, in SPE 24. So, okay, so let's have a look. So in SPE 24, we looked at a change of variable to connect the geometric and general forms. So what we can do is we start with the geometric form and we multiply by C0, a new variable C0. Okay, so we're going to replace the x with y over lambda. That's what we've done here. Okay, get C0 minus C0 y over lambda plus C0 T2 times y over lambda all squared equals 0. All right. Now, this, of course, is valid for any lambda, but we want a convenient lambda to ensure that this coefficient here, this coefficient of y, is C1. And we do that by just setting lambda equal to C0 over C1. Okay, then the coefficient of y becomes just minus C1. And the coefficient of y squared becomes, well, there's a t sub 2. There will be a C1 squared in the numerator, and there will just be a simple C0 in the denominator. Okay, and so now if we want to connect this with our general equation, okay, which has a C2 in here, we can do that by requiring that this coefficient C1 squared times T2 over C0 is equal to C2. So if we require that condition, if that's the connection between C2 and T2, then y will satisfy the general equation C0 minus C1y plus C2y squared equals 0. Okay, so this is a way of going from the original geometric form. Maybe I put that, just to remind you what that one is. That's that one there. Okay, maybe I'll put it here. Multiply the geometric form. 1 minus x plus t sub 2x squared equals 0 by C0. So we go from this geometric form to this general form. Okay, so we can summarize this in a theorem, I suppose, that if we have the following relation between the variable t2 and the variables c0, c1, and c2. If c1 squared over c0 times t2 equals c2, then x satisfies the original geometric equation precisely when y, which is c0 over c1 times x, okay, that's from here, y will be lambda times x, and lambda is c0 over c1. Precisely when y equals c0 over c1x satisfies c0 minus c1y plus c2y squared equals 0. Okay, so this little change of variables allows us then to apply the general formula that we have for our geometric quadratic to get a formula for the general quadratic. Okay, so what am I saying here now? So this condition, the condition may be rewritten, this condition here can be rewritten as t sub 2 equals c0 times c2 over c1 squared. So maybe we can say this in another way. So in order to solve c0 minus c1y plus c2y squared equals 0, okay, if we're starting with a general equation, what we do is we set t sub 2 equal to c0 times c2 over c1 squared. Okay, and then we find a solution to this associated but simpler geometric quadratic, which is 1 minus x plus t sub 2x squared equals 0. Okay, so we solve this thing for x, and then to get the original y, we multiply it by c0 over c1. Okay, so what does that amount to? Okay, so we've seen what the solution to this geometric equation is. That was x equals the sum over m2 of r of m2 times t sub 2 m squared, this Catalan type power series. Okay, so what we're saying is that we are going to replace the t2 with this c0, c2 over c1 squared. So we just put that in there. We get this expression here. Okay, and then y is obtained by taking this thing and multiplying it by c0, c1. So c0 over c1 times this thing here. Okay, and what is that? Well, we can bring the c0 and c1 inside. So we get summation m sub 2 equals 0 onwards. R of m2. Okay, now expanding this out, we get c0 to the 1 plus m2, c sub 2 to the m2, over c1 to the 1 plus 2m2. And if we want to be completely specific and write everything out, that's the sum over m2 of the r of m2, that's the Catalan number, which is 2m2 factorial over 1 plus m2 factorial times m2 factorial, also on the bottom, and then times c0 to the 1 plus m2, c2 to the m2, and c1 to the 1 plus 2m2. Okay, so what we can do is we can just actually write that out if we want to. So if we just expand it all out in terms of the Catalan things, then this is what it looks like. Okay, we're getting increasing powers of c0 and c2 in the numerator, increasing powers of c1 in the denominator, sort of going up a little bit faster because there's powers of 2 here. And of course, these exponents that are appearing here are closely connected with the factorials that appear sort of oppositely. So the 1 plus m2 is reflected by that 1 plus m2 factorial. That m2 is reflected by that m2 factorial. And that 1 plus 2m2 is almost reflected by that 2m2 factorial. There's just sort of one less, reflecting the fact that this is a submultinomial coefficient. So this thing here is not that hard to remember, if you remember the connection between the factorials and the exponents. Okay, so what is this? So this is then a direct consequence of our fundamental RSP kind of generating function, okay, except that we've taken that and cut it right down to just having the quadratic. So we're disregarding all higher order terms. We just have m sub 2's. And we're making this scaling change of variables that allows us to move from the geometric equation to the general one. And we might, sort of to close the circle, we might compare this with what we got in our very second lecture, okay? So compare this with our result from SPE2. That was the quadratic equation t plus c1x plus c2x squared equals 0 has solutions, and then we wrote down this thing here. It's just copied from SPE2. So what we're seeing here is essentially the same thing, except that when we started out, what we did is we said, well, let's see if we can find a power series in C0. We call C0 T. Okay, but this T here is really just the same as C0, so you could plug the C0 in for t. And then you're going to get exactly this thing here, except that there's a minus sign appearing throughout. Okay, so the minus sign is sort of covered by the fact that we're actually working with this geometric form where there's a crucial minus sign here that makes it all nicer. Okay, so we understand now the form of a general quadratic. Okay, but let's just observe that this more general form is not so easy, in the sense that it's not a power series. Okay, it's a series with some of the terms appearing in the denominator. So it's like a rational power series or something, perhaps you might say. And also, let's observe that this solution crucially depends on C1 not equaling 0. So let's put that assumption. Under the assumption that C sub 1 does not equal 0. If C1 is equal to 0, then we're talking about a quadratic equation essentially of the form x squared equals something. Okay, that's actually the quadratic equation that is responsible for a square root solution. So our solution and this general orientation is in some sense almost opposite the usual one. It's important to appreciate that. The usual one relies on a square root. What we're doing here is we're going far away from the square root equation. We're saying that the simplest equation is not the case when C1 is 0. That's not the simplest. That's actually the most complicated, because if C1 is 0, then we have to do something else. Then our solution here has to be modified. We have to do something additional. That's more work. So you see, this is a very different point of view. And you could say, all right, well, this is far beyond high school algebra. Yes, that's true. Let me make two comments about that. First of all, the high school algebra approach, which is how we started the lecture, implicitly assumes that you have a separate algorithm somewhere for calculating square roots. All right? That's the crucial thing. That if you don't know how to calculate square roots, then you have difficulty using the quadratic formula. Okay. This method that we're doing here does not require you to have a separate algorithm for computing square roots. And you can think about this series is like a replacement for an algorithm for computing square roots. And in fact, it can be used exactly for that. It provides an important alternative to the usual algorithms for calculating square roots. And the second important note to make, okay, is that this may appear more complicated, but it directly is now generalizable to the general polynomial equation. Okay, the usual story with square roots, we have talked already about the enormous challenges in jacking that up to the cubic equation and the quartic equation, and then those almost insurmountable difficulties that classical mathematicians had in trying to move to the quintic equation and beyond. Okay, I'm saying that is not the right way of thinking. This is I shouldn't say the right way of thinking, but it is a more right way of thinking, because we know that the technology that we have here generalizes to the general polynomial equation. Now, this has been a great review because I wanted to remind you of this scaling sort of trick that we're using to going from the geometric form to the more general one. And this is going to be really important as we try to navigate how to find numerical solutions. Okay, so that's going to be our next goal, is to try to see how we can wrestle the quadratic equation to the ground numerically, how we can get numerical solutions. course, we can't expect to get exact numerical solutions. It's intrinsically an approximate situation. But nevertheless, we still want to have a technology for getting approximate zeros to quadratic equations.